Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Who's a senior lecturer at the School of Computer Science and Informatics at University College Dublin. He has his undergraduate degree from CMU and did his PhD, as Eric said, under Dan Weld at University of Washington. And he has a large research group which works on email and many other machine learning oriented topics. So thanks very much for coming to talk to us today.
Well, thank you. I guess some sort of bag of words approach would have retrieved me. There was a few facts wrong. It was in '97, I guess I finished, but again, a sort of shallow bag of words approach would have retrieved me, I guess. So yeah, I'm going to talk today about some work on email and specifically activities in email. And my background is basically sort of applied machine learning applied to a whole bunch of tasks related to information retrieval, some text analysis, natural language processing sort of problems. This is about email. So what is an activity? Let's start there. Here's a whole collection of examples of what I mean by an activity, and I'll drill down on just one, which is suppose you want to buy a new laptop. Within your enterprise, there might be some sort of process you're meant to go through for coming up with a specification and discussing getting quotes, getting your manager to authorize this purchase, and then there's the whole payment end of it where you have to prepare an invoice, and that comes has to go through payment or something like that. So there is some process that unfolds, and maybe it's more or less formalized and automated depending upon your organization. These are all the email messages that I got when I bought that laptop, actually. I worked with a pretty inept, purchased my laptop from a fairly inept supplier, so there was sort of more email than there ought to have been. But there's email, there's a bunch of web pages, there's documents of various sorts. So there is this thing in my head when I was going through this called the activity of buying my laptop. But of course my web browser didn't know anything about that abstract entity, and neither did my email system, and of course these documents don't know that they belong to this abstraction called the activity or the task of buying a laptop. And so this work is all about trying to build the ability to recognize, detect, and track activities as they unfold, activities like this. So of course, let's just start, kind of unwind a little bit here. What is email for? I mean, originally the idea was we were just going to send messages to each other, and now we do very bizarre things like use email as some sort of very broken distributed file system where you send copies of a document and then you go back through your old email, and if you want to do version control or something like that. I mean, it works maybe. This is certainly not the kind of thing that was intended when email was being developed. Meeting scheduling, to-do lists, you often send email to yourself. Again, not the kind of thing that was anticipated when people were designing emails. Why would you bother to send a message to yourself? People do it all the time. We're going to talk today about managing activities. So today, this is my favorite email client, maybe not yours. This is Thunderbird. This is, there's nothing special at all about this. This is just the standard message view. And suppose you're participating in a bunch of eBay auctions. Maybe you're buying something from Amazon. Maybe you're scheduling some meetings. You're passing some documents around. A whole bunch of messages come into your email client. And it's up to you to, well, perhaps you want to go to the trouble of assigning keywords and putting together some filters to automatically route messages. So you might have the word eBay, and anything that comes from eBay gets put into a special folder and so on. But that's a lot of work, and most people don't do that. Instead, you're forced to somehow manually trawl through this, maybe come up with, there's a little search box here, so that might help. Here is email client. Well, let's say it's a virtual overlay over that of the existing email client called the email activity assistant, which I've been developing with a few colleagues over the last year or so, where we have these virtual folders. So for example, there's an eBay folder which contains all the eBay messages, and then the key point is that then there are individual instances of activities relating to eBay, in this case auctions. So these 4 messages relate to one auction, and well, you can't see much, but there's another one here. We have all the Amazon activities, again indexed by and visualized by specific activity. So this is the kind of first cut at what you could do, how you could show users email, how you could visualize email if your email client knew about these activities. So behind this interface is a bunch of clustering, text classification. Well, that's what I'm going to talk about today, is the smarts that are behind this interface. So once we've got this activity-centric metadata, we could visualize it this way. Maybe users wouldn't. I'm not trying to sell you on this particular kind of interface, but you have to imagine that if you had this activity-centric metadata, you could do something useful with it. So that was all by way of sort of introduction. What I'm going to talk about today is 2 particular instances of this problem. First, we're going to talk about what I would describe as highly structured activities. So the eBay, Amazon example, where basically you have a computer sending you email, and the problem is you have too many computers sending you email. You have highly structured messages where the messages relate to one another in some very well specifiable way. We'll see that in a moment. But again, your email client doesn't know anything about that structure. So the particular kind of technical ideas that are going to come up, we're going to see some work on clustering that we've done for this problem, and text classification and grammar induction. This will all, I hope, unfold over the next half hour or so, 20 minutes. Then I'm going to talk about the other end of the spectrum. So these are all highly structured messages sent from a computer to a person. Of course, most of the email you get is a person sending an email to another person. And so there's certainly plenty of messages which you would not want to characterize as activities. They're just one-off messages giving you a piece of information, or they're activities in only the most trivial sense. But there's other sort of conversations you have. I don't want to use the word threads or something. We'll see why. I'm sure it's obvious, because they don't correspond to threads. There's other sort of conversations you have which involve things like, for example, collaboratively editing documents, where there is some well-defined or well-ish defined process. You know, I've got the lock on this file, and you have to wait until I release it, and so on. Even though, of course, that doesn't. It's just a convention that we agree to act as if there was a real lock on this file, and so on. So we're going to talk about email, human-to-human email, to distinguish it from this more structured sort of thing. Here we're going to formalize the sort of technical ideas that are going to come out have to do with collective classification of messages. We're going to be classifying messages, and we'll see how this comes about. Just to acknowledge first some collaborators. This is work that I've done, as I said, for the last 2 years, basically, with a few different collaborators. The 2 primary people who've been involved in this work would be Tessa Lau, who's down at IBM in Almaden, and then Renat Kushanov, who was a PhD student and then a postdoc and has now moved on to the University of Portsmouth. And then just to acknowledge my funding agencies, there's a really fantastic Irish government agency called Science Foundation Ireland, which provided most of the funding. There's also funding from ONR, and then IBM contributed to some extent as well. Okay, so this is a web grocery store that I'm sure many of you have shopped there, or you could imagine, you maybe certainly would have heard of it. FreshDirect is a web grocery store. And when you make an order at FreshDirect, the first thing you get is this message saying, "Thank you for your order." And then you get a message saying, "You forgot to buy the cream cheese." And so you get this message saying, "We've updated your order." And then finally, and we have in our data, we'll see the experiments we've run, we have examples where these are all Tessa Lau's grocery orders, so you can go in and see exactly what what kind of person she is by the fact that she bought strawberry yogurt. What does that tell you about her? Organic brown eggs. Now that says something. There's cases where she made multiple, where there's maybe half a dozen of these modifications, and then finally a message saying, the groceries are in the truck, they're going to arrive soon. So here, this is the data. Here is a little model of what's going on. We have a finite state machine where edges correspond to messages that show up in your mailbox. So this edge, here's the state where you have yet to place your order. You go to the website, place your order, and then you transition to this state where the order has been placed and a message shows up saying thank you for your order. And then you can spin around here modifying your order, but at some point they actually deliver it. And then sometimes the garlic is moldy or whatever it is, and you complain, and then they apologize, and maybe you say that wasn't good enough or something like that. So there can be some conversation down here. So this is it's obviously a terrible model of Fresh Direct in terms of, from Fresh Direct's perspective, but in terms of the email that arrives in your mailbox, this is a pretty reasonable approximation to what's going on. And if your email client had this structure, knew about this structure, then you could imagine how it would be able to do a much better job of explaining to you the status of your Fresh Direct orders and so on. Here's the model just to show you that this is not completely crazy. This is the model for eBay where there's you submit your bid, and then you can submit bids, and then eventually you win the auction or you lose the auction. And if you win the auction, then there's some conversation that you might have, because sometimes this is a final state or this is the final state. Sometimes you have this conversation about arranging payment. So just to make this a little bit more generic, so we're talking about modeling email, structured email conversations, sequences of email messages. We're going to model them with a finite state machine where states correspond to whatever it is that's changing over time, whatever this actual process is. And edges correspond to messages that show up in your mailbox that indicate a state, that the state has changed. And so then the questions we've been focusing on are basically, if I give you a set of data, the messages, without, well, we'll see the results, but ideally without any human intervention at all, can we automatically learn that process model from a sample of transactions from eBay, a sample of auctions from eBay? Can we learn the eBay process model, for example?
A question of so the direct edits that you have,
Mm-hmm.
they don't do any encoding of which direction the email is supposed to go. An email is supposed to go.
That's right. And in fact, in this case, all of these messages are sent from Fresh Direct to me, except for this one, which is sent from me to Fresh Direct, and that isn't. No, there is. So this is a perfect example of why this is a very, it's a partial model of what's going on, but still probably a very valuable one. So we're not modeling in this here all the other things that go on, like going to a website and filling in a form and clicking go. So that happens. That's also something that happened that's something that could be associated with this activity, is the web page that kicked off your order. All we're modeling here is just the email messages. I think it's a great question for how you would extend this to handle. The promise at the beginning, remember, was about email, web, data, whatever it is, and integrating all of these applications. I think that for web forms, I think it's just a matter, I think that this is general enough and you could handle it, but we don't worry about that now. That's for sure. Okay, so how are we going to learn these process models? Here's how we're going to do it. We decompose this into 3 tasks. So let me just explain this fairly ugly diagram. We start with a set of messages. So this is your inbox or your archive of messages or whatever. There's 5 messages, suppose. And the first thing we have to do is to segment, to partition these messages into different activities. So these messages correspond to one auction that you're involved with, and these messages correspond to a second auction. Again, without any human intervention, we want to be able to distinguish, to pull the messages apart, split them up according to activity. I suppose there's a bit of terminology. We could talk about activities and types and instances of activities. I hope it's clear. I mean, there's a type of activity called an auction at eBay, and there are 2 instances of it, something like that. The next step is to identify the transitions. I'm going to explain that in a little bit more detail in a second with some examples and so on. Basically, we're going to partition the messages again. What we're interested in is basically what step of the process do these, to realize the fact that these 2 messages correspond to the same step in the process. So if you notice, M1 and M3 are both the first message in their activities. And so that's, well, we're going to try to figure this out, would sort of suggest that in the case of a fresh direct order, that this is the cluster of messages that correspond to that initial thank you for your order message. And then finally, once we have the activities and we can label these messages, individual messages, with what step in the process they correspond to, then we can try to learn this automaton. So I'm going to go through these various things, these various pieces again. So again, I think this one hopefully is fairly straightforward. We have a set of messages and we're trying to split them into activities. So maybe to adopt another example, suppose these 2 messages correspond to getting a new telephone for John. He requests a new telephone. These 2 messages correspond to Sally wants a new laptop. And I'm going to tell you briefly how we do this in a second. I just want to get the task decomposition straight first. Transitions correspond to steps in the process that we're trying to discover. So maybe messages 1 and 3 correspond to an acknowledgement of the request. Messages 2 and 5 correspond to a confirmation that this thing you requested has been delivered. And then maybe 4 is in its own little cluster. That corresponds to an optional step, let's suppose, where if you want to request something that's very expensive, then you have to get your manager to authorize it or something like that. Or you have to explain why you should get it or whatever. So there's some extra step in that second activity. So again, I think I just want to make sure it's clear. Maybe it's obvious, but just in case it's not. If we consider these 3 messages, this is sort of thank you for ordering one particular book, thank you for ordering another book, and you will soon get this book. Then these 2 messages correspond to the same transition, the same step, but for different purchases, whereas these 2 messages correspond to different steps in the same activity. So that's the kind of key distinction. We're clustering messages, but along 2, well, more or less orthogonal dimensions. So the way we do this is basically we just treat this as a clustering problem, and we just plug in 2 different distance metrics depending upon whether we're trying to get activities or all the messages for a given activity or all the messages corresponding to a given step across all the activities. So if we're trying to get activities, then we use a couple of sort of reasonable heuristics. The most important one for sure is that in any sort of structured process like this, there's invariably going to be some sort of unique identifier associated with some instance of an activity. So every eBay auction has some unique ID. And we certainly don't want to have to hardwire the regular expression to find that ID for eBay and then hardwire another regular expression for Amazon and so on. So instead we have quite a generic regular expression which we expect will retrieve all the unique IDs, the real ones, and probably also some extra junk. So it's going to be high recall, low precision, and use all those plausible transaction IDs. And it just sort of works out that if we incorrectly think that this string of symbols is the transaction ID, the chance that it will match some other random string of symbols that were incorrectly extracted from some other activity are pretty low. So this works just fine.
Is that your only variable you're clustering on? I mean, if I send out a mail to my manager saying about that new laptop, but I do have a unique ID in the order that's ongoing, can those not be clustered together?
The techniques that I'm describing now are going to require that ID to be in there, and if they aren't, they'll get into trouble. The second half of the talk, where we have conversations between people who are not going to be bothered to type in these unique IDs, are meant to handle that case, which is obviously a very important one. So for transitions, we're trying to find out, say, that what do these two messages have in common? If you sort of look at it and squint, they have some sort of template with the content, what it actually is that you purchased or what you requested or whatever is the thing that changes. So there's all this stuff that they have in common, and then you get the order numbers is the thing that changes, and then this product description changes, but then it's back to being some template stuff. So basically, to find the transitions, we're looking for basically messages that have a very longest common subsequence. Not quite, because we do have to weight the terms, because sometimes, say in Fresh Direct, and you order your week's groceries, and it could be paragraph after paragraph of stuff that's kind of the same across different messages in the same activity. This can be, if we just looked at longest common subsequence, that wouldn't work. We do a sort of TF-IDF weighting to weight the words that actually show up in these subsequences. If you just use? The problem there would be multiple activities in the same from the same sender that are going on at the same time. So 2 eBay auctions at the same time. I think that's the problem. And so it's maybe unlikely that you're going to be ordering too many books at once. I mean, if you were, then you'd sort of collapse them into one order. With eBay, I think it's more plausible why they'd be overlapping. And I guess just to take that question and turn it into a bit of a discussion about the motivation, we're not exactly motivated by e-commerce per se. I think that's a great example where it's easy to get the data, and it has a lot of intuitive value and so on. But the idea would be that within whatever enterprise, say IBM, who were very involved with some of this work, there are these automated email systems which conform to these various assumptions, where you certainly get lots and lots of instances at a time. So I think the stories are that a typical manager at IBM will be involved with many versions of these instances of these processes simultaneously. Like there's quarterly reports due, and so they manage 25 people, and they get 25 instances of this thing all going on at once. So the we do not. We do use it. Yes, we use it as a feature that's so obvious that I didn't actually put it down in a certain way. Like it's exactly your intuition. Before any of this happens, we take the Amazon messages and the eBay messages and put them into different piles and run this analysis separately. So that doesn't solve the problem, as I said, because you could have overlapping eBay messages, eBay auctions, say. But absolutely. There was a question in the back?
I'll get it.
It's not perfect, that's for sure, and especially within eBay, like you get this PayPal stuff mixed in, and I don't remember what we did. We used some automatic process for partitioning based on sender, and then realizing that two senders are actually the same sender, and I forget what heuristic we used, but that was basically it's to get at this problem. I mean, I wouldn't claim that's a kind of comprehensive approach. It's the sort of thing where it's probably pretty easy to just figure out and give the method all the various domains from which eBay-related messages will appear, and you could just hand that to the system. So I'm sort of going for one extreme, which is let's try to do everything automatically. That's an extreme position, and in plenty of applications, especially sort of consumer-oriented ones like this, it might not be, that extreme position might not be the right one, most effective. Okay, so we have identified the activities, and we've identified the transitions. Now we're going to try to learn this automaton itself, and that's, in a sense, kind of what we've been waiting for. So basically, a process model is a finite state machine, so we just have a standard instance of the automata learning problem, which of course has a very glorious history. So we have a sample of messages from some language, and we want to learn an automaton that accepts that language, and sort of not too much junk that actually isn't in L, and doesn't reject too many strings that actually are in L. So I mean, this is a heuristic problem. There's always going to be it will be impossible to know. Well, if you have a limited size sample, then you can't be sure that you've converged to the correct automaton. There's lots of algorithms out there. We chose one particular algorithm called MDI, which suits our needs. We have to deal with noise, and we only have positive examples. This is a very standard sort of constraints that come up in these algorithms. There's nothing specific about MDI, I think, that makes it the right algorithm. We probably could have chosen something else. So the way this works, we have our activities and we have our transitions. We're going to use those to generate our sample. So there's going to be one sample per activity. And the way we generate the strings, so these, I haven't mentioned, these PQR, these are just made up symbols. They're simply identifiers for these various clusters, some shorthand identifier for these various clusters. They don't mean anything. Sorry, they mean something, but the system doesn't know what they mean, if you will. So this string PQ, we get that from saying that, well, we have this activity M1 followed by M2, and M1 is a P, and M2 is a Q. We generate a sequence of those, one per activity, and then we feed that sequence of positive examples of the automaton we're trying to learn to our automata learning algorithm, and out comes the automaton. So the challenge here is, how many states should this automaton have? How many edges? Should PRRQ be accepted? Is that supposed to be valid or not? That's the job of the learning algorithm, is to, of MDI, say, to use some heuristics to make one decision or the other. Obviously, in this case, the algorithm has decided that PRRQ should be accepted, so is this not a realistic enough, not a good enough model of the process? Well, it depends what you're doing with it. If you really wanted a formal specification of this process, it's probably not good enough. But if all you want to do is use that to visualize messages for some particular client, the fact that this is strictly speaking wrong is maybe okay. Okay, so let me just quickly talk about some experiments. We, as I said, ran tried out our methods with e-commerce data just because it's easy to get and sort of intuitive and so on. We certainly, by any sort of machine learning scale, have very little data. And I suppose the point here is, I mean, we would have liked to have more data. It's hard enough to gather, even though it's we don't have much data, there's no doubt about it, but in a way, it's almost good that we don't have very much data in some sort of funny sense, which is that the average user, okay, even the person who's involved in lots and lots of instances of this activity, I mean, they have 25 employees a year and they're doing their quarterly reports, so we're never going to have millions of bits of training data here. If our methods relied on piles of training data, that would be a disaster because the average end user just doesn't buy that many things from Amazon or whatever. So in a way, it's kind of good that our results show that our learning methods can scale down to the ordinary user's desktop. Normally, you think about scaling up to the web or whatever. Here we have people even who get a lot of email. Well, they only get a couple of hundred messages a day. That would be a very busy email user. Okay. So, just to give you a few of the results, about 85% of the time, this is sort of a pipeline here. So about 84 or so % of the time, we can correctly segment the messages into activities, which is good, maybe not good enough. You might have thought that since we have these unique IDs, we really should be able to do a better job. There are certainly some cases like when the person complains about the moldy garlic that they're not forced. If they hit the reply button, then maybe that unique ID gets in there, but it doesn't always. What happens is that we often do very well, but there are some processes that use that unique ID in a less reliable way. Again, this is completely unsupervised, so you could imagine that if people gave any sort of feedback, like, by the way, I'm buying something new from Amazon today, you could exploit that little hint to try to guess that maybe this is a new activity and maybe do better. This is by unsupervised, I mean no input from the user. We're doing quite well in terms of identifying the transitions. That is, go ahead.
You said no input from the user, but you did actually tell it which so you gave it like a list of 111 e-commerce activities. Like you didn't give that a full user's mailbox.
That's
right?
correct. Right. That's absolutely correct.
So you gave the system 111 messages. Did you categorize them by the 6?
No, that was done automatically based on.
So the input is 111 messages.
Right. Right.
Okay. And these are messages in both directions?
Most of them would be from the computer to the human, but there are a few. And I think it's probably fair to say that when there are those outgoing messages, that's the cases maybe where we're missing them. When I say, so we have these 5 messages are supposed to be an activity, and we leave one out. We say it's in its own activity or whatever. How do we count that? Is that 4/5 of the right answer? How do you exactly measure that? So when I say accuracy here, it doesn't mean % of activities that are completely correct. We define a precision and recall-like metric for comparing the gold standard clustering with the clustering that the algorithm came up with, and then that accuracy is just a shorthand for F1 of that precision recall-like measure. Okay, so 90% of the time or more, we're able to identify the steps in the process. What's nice is that this is without any human intervention. If we assume, this line means, suppose that the user corrects any mistakes that might have occurred here, then how do we do? And we do better. As you'd expect, we do a little bit better, but we don't do that much better. So I think they're just genuinely, this can be a hard problem for some vendors. These ranges here correspond to the different, whatever it was, 6 different vendors. So again, in some cases, we're doing a perfectly good job, and this improvement was quite dramatic. The ability to do this for the very worst case. And then finally, how well can we learn the model? Now here, we could talk about it later. I won't go into the definition, the details of how we take the learned automaton and the automaton we were supposed to learn and know if they're agreeing. It turns out to be pretty subtle how to do that. So this is a measure called accuracy, how much the models agree. Again, talk about how we do that, but I just sort of take it that there is some measure. And when we don't have any feedback from the user, we're not doing all that well, that's for sure. And then with some additional feedback that is correcting any mistakes that might have been made up here, we do, we're up at around 66%. It's interesting to see this range. So we are doing really well in some cases. The problem is really eBay, that really kind of large and complicated model, which has these strange things with different domains where the messages might come from you and so on. We're actually doing really badly there. So when you throw out eBay, we're actually doing, reasonably, let's say. But the real thing is not do we get the right process model or even do we get the right transitions or activities. What we really want to do is provide some value to the user. So can we actually populate a little element in the UI that the user finds useful? And we may, well, these results suggest that we can tell the user something interesting about these processes even if we get the process model wrong. We're obviously making lots of mistakes with the process model, but maybe we can provide valuable information anyway. So, for example, the user might want to know, here's this process, what's the expected next state of that process? And even if we have some details of the process model wrong, or we sometimes got the activities jumbled up, 90% of the time we can actually make the correct prediction about what the next state is.
What would that mean, right? So these states don't have labels. So when you say you say, what does it mean you can tell the user what the expected state is?
We have the gold standard automaton
Yeah.
that we're comparing against. We have the state in the learned automaton that is most similar to it in the sense that there will be some disagreement, but some differences. But this is a bunch of messages came in. You get to this state by these messages. Now let's look at all the states over here. Let's find the state that's most similar in the sense that it has a similar pattern of incoming messages. It might not be exactly the same, but the most similar. We're going to call the correct state in the learned automaton the one that corresponds to the correct state in the...
That wasn't really what I meant, right? So that it's sort of more of a different level question, which is this what would it look like at a UI? Is there a way to express that? In
Sure.
UI
Okay, that actually comes over here. Let me just answer your question in a second.
Okay.
Just to say a special case of predicting the next state is predicting is there no next state. So this is basically a really nice result, I think. It says that almost all the time we can distinguish between activities that are done and activities that aren't done. And that, I think, is a fairly nice result. Again, we can be making all sorts of mistakes along the way, but most of the time we can tell is this activity expired or not. To get back to your question, Josh, this, maybe message overlap is the wrong way to describe it. What we're doing here is saying, suppose we want to explain to the user what this state means. And our explanation is going to be in the form of messages coming into this state from activities that have already been completed. So presumably you sort of understand these messages. If we want to think about describing a state in terms of messages like these that you've already seen, then what fraction of the time can we retrieve the right messages and not show someone the wrong messages? That's a first approximation for how you might explain the meaning of a state to someone is by showing them messages corresponding to transitions into that state. You could then imagine taking all that text and distilling it down and so on. But if this number means just do we retrieve the right messages? I didn't say there's various ways you can configure the system. The numbers that are circled here are all where there's no input from the user at all. The other dimensions are some additional feedback from the user. Okay, so let me move on to the other 80% of your mailbox, if you will. So email conversations with other people. So here's a few sort of examples. I mean, I'm sure this is all fairly obvious. There are all sorts of classes of conversations you have with other people, and you could imagine that they have some sort of structure, like you send request to have a meeting, and then you're waiting for the person to confirm. Or you're editing a document and you hand off your version and you're waiting for it to come back to you, and so on. So we do not try to model these sort of activities with automata as we did before. I mean, maybe that's just impossible. Maybe these sort of activities are so that every instance is so different from any other instance that we shouldn't try. But I think there are some cases where you could imagine some fairly simple process model that handles actually a non-trivial collection of your human-to-human conversations. And maybe these are some examples. But what we can still do is group messages according to activities. We can still try to take an incoming message and put it into at least a virtual folder called editing this document or planning that trip or whatever. And then more interestingly, we're going to try to label messages with, well, I'll just use a couple of cryptic words, the sender's intent. So this has to do with an idea called speech acts that comes from philosophy of language and so on from years ago. So the idea would be, and just to be clear, this is work initiated by William Cohen and some colleagues a couple of years ago. The idea is to sort of label messages with some abstract, very generic description like, this is a message that requests a meeting, or that delivers some data, or that commits to taking some action. So here's a couple of examples where we're requesting something. And you could imagine that if your email client knew this was a request, some sort of generic request, then it could add it to your virtual to-do list saying, well, you requested something, do you want me to monitor for when the response to that request comes in? Or it's been 2 weeks since you've submitted this request, do you want me to follow up, or something like that. So before we get to, so this is what we're going to try to do. Partition messages into activities and label messages with these generic speech acts. So I think it's probably obvious, but just to make it clear, we can't use threads for this. We can't use folders for this. Threads and folders don't solve the problem of partitioning messages into activities. I think probably everyone would buy that, or should I try to justify that some more? I think it's also a lot more than keyword search. So just because you have a great index over your messages, it's still a human who has to come up with the keyword, the word that's likely to trick the system into coming up with the right messages and not all the other ones that happen to have the obvious word. So I don't know, I find myself doing this of coming up with a search term which is not obviously the right search term, but I pick it because it's going to the right search term has plenty of recall but low precision, and so you have to find the other search term which also has high precision but high recall but good precision. So basically, any sort of search-based interface, well, that's just pushing the problem back onto the person of having them come up with these search terms. And then, even if you did find the right keywords or time window and so on, we still aren't any closer to providing these sort of high-value query capabilities like roll back one version on the document I'm editing, or tell me all the auctions I'm participating in that I've been outbid, or automatic to-do list management, and so on. Okay, so just to give an example of these speech acts, this is a sample of the data that we actually used. We'll see some details later. These are messages sent by a bunch of people pretending to run some company, be involved in some project within a company. It was a simulation. It's real-ish data. It's real messages sent by people, but there's no real company. There's no real architecture for which an updated architecture chart is being requested. They're just pretending. This is gathered as part of a large DARPA project, ongoing DARPA project. I'll tell you a bit more about it in a second. So this message is requesting something and delivering an opinion. I think we can manage the rest. That's why this is seen as giving someone's opinion. Can you send me the updated architecture chart? That's requesting something. Then maybe the message comes back saying, here it is, here's the updated architecture diagram. Then there's a follow-on which says, that's great, now can you do this other thing for me? This other thing being gussying these up a bit. So you can imagine this is a fairly complicated text classification problem when you have to deal with things like that. And then there's the response to that comes back, and then finally an opinion. We should be able to take care of that. So I don't want to try to sell you on these particular speech acts. The intent is that something like this is in the ballpark. This idea of speech acts is a fairly, well, I'd say, intuitively useful idea, and then we could discuss which particular set of speech acts would be useful for which classes of users and activities and so on. So the key idea here, as I said, Cohen and his colleagues have been exploring the idea of attaching speech acts to messages for a while. The key idea here is that activity identification and speech act labeling are actually complementary tasks. So what we're going to do, I'll give you some details in a second, but if we knew, for example, that two messages are in the same activity, then that would give you some hints about what the correct speech acts are. I'll try to give you some intuition for that in a second. And by the same token, if we somehow are confident of the speech act distribution for some messages, then that might tell you something about how those messages segment themselves into activities. So what we do is we make some initial guesses for the activities in the speech acts, and then iteratively tune them up based on the current guesses for the other guy, and we just go around that loop until things converge. So just the intuition here, if we know that this message and this message are in the same activity, somehow we've decided that these are likely to be in the same activity, and we know that this is a request, then it somehow makes it more likely that this is a commitment. When you ask someone to do something, if they quickly follow up, then they're probably saying, yes, I will do that. So there probably is some sort of correlation over time between these speech acts within an activity, and the goal is to try to learn that. And by the same token, if we know that this is a request and this is a commitment, but we don't know whether they're in the same activity, then that makes it more likely that they're in the same activity. We can make a connection between these two messages.
When you're talking about commitment request, that's just a piece of that email, right? It's not the whole email.
Right. Let's make this very simple. So suppose we're not, the speech acts were in terms of nouns and verbs, and suppose just for the sake of the simple example, we'll just focus on the verbs. So requesting what? Well, let's forget about what they're requesting. Let's say all we wanted to do was focus on requesting and commitments. Okay, so as I said, here's our algorithm for classifying messages according to speech acts, and at the same time segmenting messages into activities. So we start with some initial guesses, and then we iterate, where I'll tell you on the next couple of slides how we take a given best guess for the activities and use that to try to tune up the speech acts, and then take the current best guess for the speech acts and try to do a little bit better on the next guess for the activities. So the initialization is not all that interesting. We use a simple bag of words distance metric, and then just cluster the messages to try to find activities with a few email-specific heuristics, but nothing that you wouldn't expect. Interestingly, this works better than using threads. So if you actually, there is a thread structure in those conversations, and if you just use threads and activities are the connected components of threads, something like this, then the activities you get out are not as close to the real thing as using something like this. I mean, that's probably an artifact of this particular data set. There are some threads in there, and maybe because it's simulated data, maybe people were told to not use threads as make sure you don't always just reply to things, something like that. I don't know the details. I'm not going to say that this is always going to be better than threads, but in this data, it was. Finally, speech acts, we just use, again, a bag of words representation with we use an SVM. I think I'm not going to say that's obviously the right classification algorithm. It probably doesn't matter what you use. So how do we tune up the activities, the speech acts from the activities? So the idea is we have some training data, we have some activities, and here's one and here's another one, and we can use this to train a classifier. This classifier is going to classify a given message into its going to give you the speech act of a given message. And all we're going to do is, we look at the other messages in the same activity and get their speech acts. So remember, these letters stand for various different speech acts, I guess. Deliver, request, commit, deliver, something like that. Promise, I don't know. So we basically say, here's a bag of words for this message. We're trying to find out, is this a deliver or request or whatever? And then we look at the speech acts of the message upstream and downstream in that same activity. And these are all features that are given to an SVM. So now we can say, look at this. This is an activity that's just unfolding. We have this particular message here. And is it likely that we would have a commitment followed by another commitment? Maybe the bag of words here looks like a commitment, but because of the commitment up here, it's maybe unlikely in the training data that you see a commitment followed by another commitment, so we'll decide that this is actually a delivery or something like that. Go ahead.
Sorry, I still don't understand. So for a given message, do you assume that it only belongs to one activity? That it really can't reference two activities?
Yes.
Okay.
Which is a problem. Some more experiments I'm not going to talk about today. We're trying to relax that assumption. I mean, it's a sort of a reasonable approximation, maybe. I think it's really hard to solve that for real. But we're looking at another data set, real data, and you do have this problem that a given message belongs genuinely to two different activities. Any normal human being would say this message belongs simultaneously about two distinct activities. And so we are having to deal with that there, but not here. I suppose, what we could do is have, what are the ancestors? You could have the ancestors be basically a distribution over all the messages you know about, rather than sort of discretize that as, yes, you're an ancestor, no, you're not. You could actually have loads of other messages, all the other messages in your mailbox, but with these features weighted. Yes, the previous message in this activity was a commitment, but I don't actually think it was really in this activity very much. Maybe that would be a more effective, give you a slight boost. I don't know. Okay, so the last piece of this puzzle is we have a guess for the speech acts, and we want to use that to tune up the activities. So again, we have a training process where we assume we have some known activities. What we're going to try to do is learn to classify edges. So now we finally see why we've thought about activities as basically edges, and then activities are just the connected components of those edges. So what we're going to do is look at this edge and learn to classify this edge as a good edge, but that edge as a bad edge. So we come up with positive and negative examples of edges that we want. Within an activity, that would be a yes, and across activities, that would be a no. The features we use are the bag of words similarity of the two messages. So that's a kind of an obvious thing you don't want to throw away. This is talking about the new laptop, and this is talking about the new telephone, and so that should make you think they're in different activities, of course. But we also look at the speech acts of these two messages as well. So then we have this new set of messages, and we're trying to decide, is there a link between these which make this all one big activity? We put this into our SVM, and maybe we decide to chop that link and segment this into two activities. Should I be finishing right now?
Well, soon.
Okay. Well, we're basically done. I could tell you a bit about the experiments, but it's sort of the fun part when you talk about the experiments, but maybe I'll go through them fairly quickly. So as I said, we used some simulated email, which was intended to kind of a bunch of people sort of pretending to run a company. This is part of the Kalo project, as I said. A few details about the way we ran our experiments don't really matter. Here's some results. So first of all, as far as activities go, this number here is how well we're doing at recognizing activities using the initial guess. And the answer is we're doing really quite well. So remember, this is sort of a little bit better than threading. We're doing really quite well. We let this iterative process converge, and it doesn't have very far to go. It does converge to 0.98. It gets a little bit better. There wasn't much room for improvement there. So that's quite a good result. As far as the speech acts themselves, we're sort of getting the right thing happening, where you see this iterative process does improve the accuracy of assigning these various speech acts. But the absolute performance is certainly not great. So let me just explain that in a bit more detail. First of all, we're measuring using the kappa statistic, which has to do with sort of an agreement between two sets of assignments. We used kappa because Cohen used kappa, and we wanted to be able to compare our results to his. I don't want to defend that particular way of defining performance. Each one of these curves corresponds to our ability to predict a particular speech act. This is an iterative algorithm, so this is basically time along this dimension. And what you see is that the curves more or less go up. So that's a kind of a nice, at least they don't go down. You could certainly say that. As far as the absolute numbers, though, clearly we're doing really well in some cases. So this one is delivery. We can do a pretty reasonable job of knowing that somebody is giving us a piece of data. The reason some of these ones where we're doing very badly, the distribution over these is quite skewed, and there's a lot more of some than there are of others, and I think that's part of it. This is not also not a very large corpus for the usual sort of machine learning reasons to generate the training data and so on. To manually annotate the data is a pain. So go ahead. It was annotated for speech acts. We added the annotation for activities. So in a sense, that's nice that they were done independently, which probably somehow means that's better than if they had been done by the same group, I guess. And there's just always I went through this example. Are these actually part of the same activity or not? And the way you just make your decision is by looking at another 10 or 20 messages and say, yeah, this is some coherent. But actually, it seems to have this sort of two-part structure where first you do this part and then it sort of switches. And somehow our annotator decided this was one activity. It's really an open question whether that's, how reliable. We don't have inter-annotator data. My guess is that two annotators might disagree quite a bit. This is a hard task, I'd say.
What I'm interested in is you have two of the same task, but their flow might be quite different. Might be different. Like I request something and somebody asks for clarification in one case, but in the other case they just do it right away. So you have multiple kinds of state machines again.
Yeah.
Particular activities might follow.
Right. So, I mean, I think just to pick up on a point that you said, this idea of there is no finite state machine here that's being used to comprehend these messages, but this idea of classifying based on a little bit of context is some kind of simulation of a state machine that we don't build explicitly, exactly as you say, because there probably is no one right state machine where there's as many as there are activities or something like that. but we want to get some idea of something like a state and changing to something like a different state. I think the example you mentioned certainly would happen. I don't want to kind of give you, I don't want to have to show you an example, but I think you're absolutely right. Your intuition is right that some of these correlations, like a commitment followed by a delivery, I mean, intuitively that sounds right. Some of those correlations are a lot stronger than others, that's for sure. Okay, so we're basically done. So the bigger picture, let's go back to the beginning, is about activities and making desktop applications aware of activities. I think this is a very generic, broad problem. We've certainly focused so far exclusively on email, and I guess it's an open question. How do we take these ideas and transition to bringing web pages, bringing documents, and so on into activities? A lot of interesting questions there. So the key ideas here are finite state machines as a way to model these activities, which have their problems. On the other hand, it's a fairly simple model, so we can actually try to do a reasonable job of trying to learn them. And then we've looked at kind of two ends of this spectrum, one where there's a huge amount of structure, one where there's hardly any structure or a very weak structure. Obviously, the middle ground is probably where there's a lot of interesting work to be done. I made this point already that I think for me the next piece of this is to try to incorporate other applications, not least because there is what there is in the email, and you have to believe that if you knew what web pages the user was looking at the same time or what documents they were looking at, you could bring a lot more to that message. In other words, it's not just about making a fancier demo. It's about actually you can use that data to do a much better job, I think. Okay, and that's what I have to say. Thank you.
So we have time for just a few questions.
Mm-hmm.
Do you have any thoughts on using aggregate data from multiple users for structured and for the other stuff?
Yeah.
How that might improve it or not?
I think that on one hand, in terms of the kind of core machine learning task, more data, better, gonna do better. I guess there's two things that argue against it, though. One is privacy. So one of the things that's hard about doing email research is getting real data, and because people don't want to donate their data. Now, sometimes maybe within an enterprise, they own your email, and you can just say, we will aggregate your data. That's all there is to it. But how far can you push that? I think you have to be adding a huge amount of value before your average Hotmail customer is going to say, sure, go ahead and use my email and do whatever you want with it. Maybe it'll help someone else. You have to be adding a lot of value before someone's going to buy into that, an ordinary user. So that's one part of the answer. The other part is I think that there is a personalization angle here where these regularities between temporal order of speech acts and so on, you could certainly believe that they're different for different communities or even different users. Or what I think constitutes an activity is different from what you think constitutes an activity. There's been some sort of sociological work of just how do you use your email, and people, the term activity. I had a short paper at Chi a couple of years ago where we did this task. We gave people a pile of messages and said sort them into activities, and different people did that in a different way depending if they were managers or people down in the leaf of the organization and so on. So if you aggregate the data, you're going to have, that's good from a machine learning perspective, but maybe you lose the ability to try to deliver some sort of personalized service. Eric.
So something that I occasionally get mad about in the case application is that sometimes
the activity will stop on the machine. Very reactionary. It's not going to fail. It's the next day. It goes out. If there's a pause, I might forget about it. So no leave it to it. How well do you adapt to actually saying, oh, you missed a step, or it's been too long, this activity seems to be in hiatus?
Yeah. So while there certainly are problems, I really like the process model formalism, and as one example of what you could do, if you could pull it off, how you'd be able to use it is you have not only the trajectory, but also sort of how long individual steps take. And therefore, if we've been waiting at this state for too long, we could raise an alarm. I think that would be really, really interesting, both in terms of the sender. You might want to send a reminder, and the person who's supposed to act, put this to the top of your to-do list or turn it red or something like that. So we didn't talk at all about having time be part of this at all, except we do use time in some of the heuristics for deciding are these two messages in the same activity and so on. But actually to model at a detailed level how rapidly this process is supposed to unfold for exactly that purpose, to try to catch stuck processes. It's a great idea.
All right.
Anything
Well,
else?
thank you very much.
Okay, thank you.